Glycerol, which is also known as glycerin, has a wide range of uses. Some of the most common uses are in food products and pharmaceuticals. Biologically, glycerol is used for the storage of fat. The glycerol serves as a backbone and links to three different fatty acid molecules. The combination of the three fatty acids and the glycerol backbone is known as a triglyceride. The goal of this experiment is to break apart triglycerides, which are a major component of vegetable oils, and to recover the glycerol backbone. The method of producing glycerol this way is actually the traditional method of producing biodiesel from vegetable oil. However, I don't really have a use or interest in biodiesel, so this video is highly focused on the preparation and isolation of the glycerol. So these are the chemicals that I used for this experiment. I just used generic vegetable oil, but you can also use other oils like canola oil. The amount of hydrochloric acid and sodium hydroxide that you use will depend on the amount of crude glycerol that you make. The amount of glycerol obtained depends greatly on the oil that is used. The yield from different experiments and from different oils is probably going to be quite variable. To an Erlenmeyer flask was added 200 milliliters of methanol. This was followed by the addition of 9 grams of sodium hydroxide. This was stirred until the sodium hydroxide had dissolved. After several minutes, no sodium hydroxide pellets remained, but the solution was still cloudy, which is okay. In the meantime, while the sodium hydroxide was dissolving, 800 milliliters of vegetable oil was heated to around 50 degrees Celsius. When the vegetable oil had reached 50 degrees Celsius, the methanol sodium hydroxide solution was added to it. The methanol is immiscible with the vegetable oil, and you can see it immediately forming a layer. This can pose a problem, but to get around it, we'll simply need to use quite strong stirring. If strong stirring is not used, it will simply stay as two separate layers and the reaction won't work very well. While the temperature was maintained at around 50 degrees Celsius, the mixture was stirred for about 30 minutes. In this step, we're doing what's known as a transesterification reaction, and we're liberating the fatty acids from the glycerol backbone. The base acts as a catalyst, and for every triglyceride we produce 3 methyl esters and 1 glycerol molecule. After 30 minutes, the stirring was stopped and the mixture was allowed to settle. It should be given at least an hour to settle, but I left mine overnight. It's separated mainly into 2 different layers, where the dark lower layer is mostly glycerol and the upper layer is mostly biodiesel. The liquid portion of the upper layer, containing mostly biodiesel, was transferred to another container. This biodiesel is crude, but all that really needs to be done to it to make it useful is to wash it with a little bit of water and then to dry it. However, I'm not very interested in biodiesel, so I discarded it. You can see in the Erlenmeyer that there's a liquid portion, but there's also some chunks. The chunks are most likely gelled biodiesel, which tends to occur at some lower temperatures. At the bottom of the Erlenmeyer, I'm left with a messy mix of the gelled biodiesel and the glycerin. To separate them, I added the entire mess to a beaker. Once it was in the beaker, it was stirred and the glycerin was allowed to settle at the bottom, and when the gelled biodiesel floated to the top, it was simply scooped off using the glass stir rod. At this point, I was left with an orange crude glycerin mixture. Using pH paper, the pH was tested and it showed that it was strongly basic. To the crude glycerin was added a total of 17 milliliters of 31.45% hydrochloric acid. The addition of the hydrochloric acid will react with the base to form water and salt, which you can see precipitating out. The addition of the acid will also regenerate fatty acids from their salt form. The goal in this step was to make it strongly acidic with a pH of around 1. After the solution had been acidified, the stirring was turned off and it was allowed to settle. This took a little while, but eventually the salt settled at the bottom, and you can see here that we actually have a layer that formed at the top. The upper layer is undesired fatty acid and must be removed. The mixture was transferred to a separatory funnel, leaving as much salt as possible at the bottom of the beaker. The layers were allowed to separate, and the lower layer was removed from the upper layer. As stated before, we want the lower layer, which contains the glycerin. My glycerin layer was a little bit cloudy because some of the salt from the beaker poured in. At this point, the pH of the solution was acidic, but we want the pH of the solution to be around that of glycerol, which is around 7. To do this, the pH was adjusted using small amounts of dilute sodium hydroxide solution. This step can be a little difficult and frustrating because it's very easy to overshoot by adding too much sodium hydroxide, and then you'll have to reacidify by adding small amounts of dilute hydrochloric acid. When a pH of around 7 is achieved, the next step is to evaporate a lot of the water. The temperature was increased to about 110 degrees Celsius until the solution was reduced to about a third of its volume. As more water evaporates, the solution becomes darker and salt slowly precipitates out. When it reached about 1/3 of its volume, the stirring was stopped and the salt was allowed to settle at the bottom. The crude glycerol was then transferred to another beaker and the salt was left behind. At this point, I was left with some still very crude glycerol. The next step is to decolorize the glycerol. I dissolved the glycerol in 4 times its volume in methanol. I appeared to have roughly 20 milliliters of crude glycerol, so I added 80 milliliters of methanol. Once it had fully dissolved, 6 grams of activated charcoal was added. The activated charcoal is added to remove the colored impurities. This crude mixture likely still contains a little bit of water, so I added some molecular sieves to try to trap some out. The sieves I use here are 3A molecular sieves, which are able to selectively absorb the water. I let this mixture stir for several minutes. The molecular sieves and the activated charcoal were then vacuum filtered off. And here we are left with a nice colorless solution. The volume is greatly increased because I washed the molecular sieves and the activated charcoal several times. Now the final step was to remove the methanol, and for this I used a simple distillation. Before it became too viscous, I transferred it to a small beaker and evaporated the final amount of methanol. I heated it to about 110 C for 30 minutes to make sure that it was dry. This was the final nice clear glycerin product. In this shot, it's not as viscous because I just removed it from heat. The glycerin was then transferred to a small amber bottle for storage. The final yield of glycerol was about 24 milliliters.